So over here we've been given an equation and we've been given a point that satisfies the equation. So for the first question, all we're going to do is substitute in those values, and I get minus 2 equals 1 plus k sine pi on 6. In order to work out what sine pi on 6 is, I can use one of my special triangles, which is the equilateral triangle that's been chopped in half, and that gives us pi on 3, or 60 degrees in this angle, and then half of that, so pi on 6 over here, and because it's been chopped in half, this length is 1, so sine of pi on 6 is 1 over 2. Let's substitute that in and do some rearranging. Minus 3 is equal to k times a half, therefore k is equal to minus 6. For b, the first thing we're going to do is substitute that back into the equation. Y equals 1 minus 6 sine x. Now, I want to find the values of a and b at this maximum point. And if you look back at y, the maximum of y is going to be when sine x is as negative as it can possibly be. In fact, it's going to be when sine x is equal to minus 1. And that gives us, at that point, that y is equal to 1 plus 6, which is 7. Now the question is, where is sine x equal to minus 1 on this range? Well, over here, the value of the graph of sine goes like this, where this is 2 pi, this is pi, this is 3 pi on 2, and therefore sine x is equal to minus 1 at 3 pi on 2. So that's that x is equal to 3 pi over 2, and therefore AB is equal to 3 pi on 2, comma 7. Next question. So we need to find, first of all, an expression for the nth term. Now, if you look at this, it's an arithmetic sequence, and clearly the common difference that we're adding to it each time is going to be 18. I'll just double check that. 26 plus 18 is equal to 44. And the first term is 8. So if you have an expression for the nth term, an is equal to a plus n minus 1 times the common difference, which is equal to 8 plus 18n minus 18, which is 18n minus 10. The sum of the first n terms using sigma notation is going to be Sn is the sum from n equals, oops, we're not going to do n over here because we need to use a dummy variable. So the sum from I equals 1 to n of 18i minus 10. You could use r instead of I if you wanted to. And then finally, we want to work out the sum of the first 15 terms. Now, I think in your formula book it says something like Sn is equal to n over 2, 2a plus n minus 1d. So S15 is going to be 15 over 2, 2 times the first term plus 14 times the common difference. And this is a rare example where we haven't got a calculator to work out something slightly annoying, so we've just got to do it, and that's going to be 16 plus 14 times 18 is, well, I'm going to use my calculator, but you need to do it by hand, 252. Easier to divide both things by 2 before timesing by 15. 8 plus 126, and then you finish off the maths. And you get 8 plus 126 times 15 is 2010. There we go. Next question. Consider the functions below. I'm just going to close down my inbox. Find g of f of x. So for a part 1, I'm going to write that as g of f of x because I find that easier to think with. And what we need to do over here is we need to put f of x into g. So we get 1 over 2x plus 3. And write down the domain of the function. Well, clearly the bottom can't be equal to 0, which means I can't have 2x plus 3 equals 0, which means that x can't be equal to minus 3 over 2. So the domain, if we want to write it properly, is going to be the set of x belonging to the real numbers such that x is not equal to 3 over 2. Similar exercise for f of g of x. Over here what we're doing is we're taking all of g of x and we're putting it where the x is in there. And so we're going to get 2 times 1 over x plus 3, which I think looks nicer as 2 over x plus 3. And for the domain, it's simply the fact that x can't be equal to 0. So x is a real number such that x is not equal to 0. Find the coordinates of the points where the graphs of f of x and the graphs of g inverse of f of g of x intersect. Now over here it might help to do a little bit of rearrangement because you notice that this thing is a little bit strange. So of course you could find g inverse and substitute it in, but actually if g inverse of all of this is equal to f of x and you do g on both sides, taking g of both sides removes g inverse and gives you g of f of x. And the reason that that's nice is that we've already got an expression for g of f of x. It's this thing over here. So we can now write 1 over 2x plus 3 is equal to 2 over x plus 3. And clearly the first job in this bit of algebra is to get rid of the denominators. So I'm going to multiply both sides by x brackets 2x plus 3 and carefully cancel things as we go. Now notice you've got 3 terms. You've got this one here, and this one here, and everything needs to be multiplied by x 2x plus 3. So if we multiply the first one by x 2x plus 3, the x's cancel and we get 2 times 2x plus 3. For the 3, there's nothing to cancel out, so that's going to give us x 2x plus 3. For the 1 over term, the 2x plus 3 will cancel, and that will just leave us with x. At this stage, we want to carefully expand, and you notice that because of this thing, you're going to get a quadratic. So let's try and be sensible about putting all of the x squared and the x terms together so we don't have to write out piles of working. We get a 6x squared, and that's our x squared terms dealt with. We then get 4x from this and 9x from this, which is 13x. Take away x is 12x. And then finally we've got a constant term, which is this one, and that's plus 6 equals 0. Everything is divisible by 6. Hooray! So x squared plus 2x plus 1 equals 0, which factorizes nicely as x plus 1, whoops, let's remove that, all squared is equal to 0. So there's only going to be one solution for x, which is x equals minus 1. At this stage, I'm going to look back at the question. It says find the coordinates of this point. So to find the coordinates, I need to substitute x equals minus 1 back into one of the original ones. I think I'm going to substitute it into here. This says that y equals 2 over minus 1 plus 3, which is minus 2 plus 3, which is 1. And therefore, when we're finding coordinates, it's nicest to give the answer as xy equals minus 1, 1. Full stop. Next question. Find the area of the triangle AOP in terms of r and theta, where theta is in radians. That might be relevant later on. Now clearly this is another radius, so it's r. So the area is going to be half product of these two, r squared, sine the angle between them, theta. Done. Now I've got another triangle, so what I might do at this stage is just be careful when I write area down that I specify which triangle it is. So I'm going to write area of AOP, small letters. That distinguishes it from the area of POT, a pot. Now for POT, clearly you've got a right angle here because this is a radius meeting a tangent. But now we've got to work out either what the length of this thing is, or ideally what the length of that thing is, because then we can do half base times height, and that would tell us the area. Well, that's a theta, and that's an r, and therefore this is going to be r tan theta. And the way we remember this is that tan theta is the multiplier where if you've got the adjacent side to an angle and the opposite, tan is what you multiply the adjacent by in order to get the opposite. Sine, incidentally, is what you multiply the hypotenuse by to get the opposite, and cos is what you multiply the hypotenuse by to get the adjacent. It's always helpful to think in these multipliers. So we know that that's r tan theta, which means we've got half r squared tan theta as a pot. Using your results from parts A and B, show that sine theta is less than tan theta. Now, the results from part A and B talk about areas. So I need to think, right, I want a triple inequality, which bounds something, where the sine bit over here is less than something, which is then less than the tan bit. What could that be? Once you start thinking along these terms, you notice that you've got the area of this triangle and the area of this triangle, and there is actually a shape which is in between them, and that shape is the sector of the circle. So let's try working out what the area of the sector is. Well, the area of the sector is going to be half r squared theta, when theta is in radians. And the good news is that there's a theta there, which sort of corresponds to what we want. So, oops, it's disappeared, half r squared theta. Now, the area of AOP is definitely strictly less than the area of the sector, which is strictly less than the area of POT. And that's obvious from the picture, because the sector's got this extra bit, and that triangle's got this extra bit. So half r squared sine theta is less than half r squared theta, which is less than half r squared tan theta. And this looks great. There's a half r squared which we can divide by. Therefore, half sine theta is less than tan theta. We've always got to be a bit careful when dividing in inequalities, because you're only allowed to times or divide by something when it's positive. But if you look at this, the thing you're dividing by is half r squared theta. So it would be good to say as half r squared theta is positive, because it's a square. And in short, that's done. 2 marks. For this question, we've got a nice graph of a rational function, and we need to find the values of a, b, and c. Now, over here, let's just write down some equations of asymptotes and sort of see where we get to. Okay, we've got some asymptotes and we've got some intercepts. Let's start off with this intercept here. This is where x is equal to 0, and when x is equal to 0, y is equal to a over b, which is equal to minus 2. Therefore, a is minus 2b. That's the first equation. I'm clearly going to need 3 equations because I've got 3 variables to find. This thing is when y equals 0 and x is equal to 2. Now, if y is equal to 0, the top is equal to 0, which means a plus 2 equals 0, which means a is minus 2. And straight away you can see that if we've got that a is equal to minus 2, we can go back to this guy, and that tells us what b is. B is a over minus 2, which is 1. So, very nice. We've now got 2 of the equations. Let's take a look at the asymptote now. Now, this asymptote occurs when x is equal to minus 2. And when x equals minus 2, clearly the bottom must be equal to 0 when you've got the asymptote. So, b, which is 1, plus c times minus 2 equals 0. And that gives us an expression for c, If we rearrange this, we get c is equal to 1/2. And that is the third thing. Turns out we've not had to use the horizontal asymptote, but that's fine. Using the values of a, b, and c found in part A, sketch the graph of blah, 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 showing clearly all the intercepts and asymptotes. Now, if you take the modulus of the old y, what you get is that everything just becomes positive. Now, this was positive in the first place, so we'll stay the same. I'm just going to sketch over that. This bit was positive in the first place, so that stays the same. But this bit over here has become positive, and we just need to be careful. -2 gets mapped to 2, and then goes up to the asymptote, and there we are. And in your sketch, you've got to very carefully put in all of the asymptotes as well. So you put this thing going through -2, and you put this thing going through 2, and you do need to make sure that you show that these things asymptote. So things need to be getting closer to the line over here and closer to the line over here. Next question. H is equal to g of f of x, so let's find it. H of x involves putting g into f. Oh, no, other way around. Putting f into g. So h of x is going to be 4 over x plus 2 minus 1. Done. Find the inverse. So to find the inverse, I start off by writing this as that, and then I switch the x and y, and then I trouble myself with making y the subject. So I get x plus 1 equals 4 over y plus 2. It occurs to me that if I write it like that, I could cross these two over. So I could times both sides by y plus 2 and divide both sides by x plus 1. And then I just get y is equal to 4 over x plus 1 minus 2. And we just write that as an inverse to finish things off. Because we're not asked about x and y, we're asked about h inverse. So that's the answer. Moving on. Show that this is the case. So we're going to start off with the left-hand side and write down what that is. Sine 2 theta over 1 plus cos 2 theta. And there's only one expression really for sine 2 theta, which is 2 sine theta cos theta. However, for cos 2 theta, you've got 3 possibilities about what you might write, and it's worth being tactical about which one you use. Cos 2 theta is either cos squared theta minus sine squared theta, or it's 2 cos squared theta minus 1, or it's 1 minus 2 sine squared theta. Now if you look at this expression, there is a 1 plus on the bottom. So if we use this, then clearly we're deleting terms straight away because we're going to get 1 plus something minus 1, which is nothing. So it's worth using the second expression in the first place. 1 plus 2 cos squared theta minus 1, which is 2 sine theta cos theta, heaven, over 2 cos squared theta. The 2's will clearly cancel. Cos theta gets rid of one of those, so we get sine theta over cos theta, which is tan theta, which is the right-hand side. It then says, hence find the value of cot theta. So let's set about doing that, make some space. Of cot pi on 8 in the format blah, 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 blah. So, cot pi on 8, I need to first of all look at this. Well, it relates to this bit more clearly. It's 1 over tan of pi on 8, i.e. it's the reciprocal of tan of pi on 8. So we can just write this fraction upside down. Cos over here of 2 times the angle, which is cos pi on 4, over sine pi on 4. At this stage, I need to know about cos and sine of pi on 4, and the relevant special triangle is the one that does 1, 1, root 2. And so I get 1 plus cos of pi on 4 is 1 over root 2, sine of pi on 4 is 1 over root 2. And what we're going to do to tidy up this fraction is we're going to multiply top and bottom by root 2. And clearly, that just gives us a denominator of 1, which goes away, and we just get root 2 plus 1. And to write it in their format, which is 1 plus 1 root 2. Done. We're going to pause here, and I'm going to carry on the last 2 questions in a minute. we want to get tan x, and we're starting off with this expression. Clearly the first thing we're going to need to do is to expand things out. So here we get sine x cos alpha minus cos x sine alpha, and that's going to be equal to k multiplied by the next two terms, which are the same but with a different sign. So sine x cos alpha plus k cos x sine alpha. Now if you look at this, what we've got is some sines and some cos x's, and we want to get some tan x's. And the only thing I'm allowed to do is to do the same to both sides, or do the same to every term. And actually, in order to get rid of the cos's and turn the sines into cos's, the only thing that it's sensible to do is to divide everything by cos x. So we can clear these up, and that turns into tan x, careful, if you're like me and your x's look like alphas, tan x cos alpha minus sine alpha equals k tan x cos alpha plus k sine alpha. So now we want to find an expression for tan x, so let's put all the tan x's together and factorize. Tan x into cos alpha minus k cos alpha is equal to k sine alpha plus sine alpha, and therefore tan x is equal to that divided by that. I think it's quite nice at this stage to factorize out the k plus 1, and if we do that, actually we are going to write that as k plus 1 lots of sine alpha over 1 minus k lots of cos alpha. Hence find the values when of x between blah 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 when k is a half and alpha is equal to 210. So if we plug a half into this, we get 3 over 2 over a half. Now 3 over 2 over a half is clearly 3, divided by tan of 210, because that is equal to that. So tan x is 3 tan 210. So first of all, we can work out what tan 210 is, and this requires some knowledge of the tan graph. Now x is between 0 and 360, and so I think it makes sense to sketch out what tan looks like in those places. We've got some asymptotes for tan, which occur here, and then there's a thing, and then there's other asymptote there, and then it's going to cross here. And tan then looks like this. Remember, it's got a gradient of 1 at the origin, where this is 360, this is 180, and 210 is 30 degrees on from 180, which means tan 210 is the same as tan of 30. Tan of 30 is here. And to work out tan 30, I'm going to pull out my special triangle again, which looks like this. 30 degrees is here. You'll remember from question 1, special triangle goes to 1, and therefore that's going to be root 3. So tan of 210, which is tan of 30, is going to be 1 divided by root 3. Therefore, tan x is equal to 3 times 1 over root 3, which is root 3. And if you look at this picture again, that must mean that x is this angle here, because tan x equals root 3 over 1. So my first solution is that x is equal to 60 degrees, which is there. Now, if x is equal to 60 degrees, then I've got one more solution from x, which is this one, and that is 180 plus 60. Therefore, x is 60 or 180 plus 60, which is 60 or 240. Now, I'm afraid the fire alarm has just gone off, so I'll finish this off later on. So over here, we're told something about the third, fourth, and seventh terms of an arithmetic sequence. The third term is a plus 2d. The fourth term is a plus 3d. And the seventh term is a plus 6d. And we're told that these are the first three terms of a geometric sequence, which means to get from here to here, I've multiplied by a certain ratio, and to get from here to here, I've multiplied by the same ratio. Now, remember that the ratio of two terms also means one term divided by the next. So what this tells us is that if we divide the seventh term by the fourth term, we get the same thing as if we divide the fourth term by the third term, because this divided by this is r, and this divided by this is r, and therefore these things are equal. We can cross-multiply, kill the denominators, and we end up with an expression which says that a squared plus, if we think about it, we get 6ad plus 2ad is 8ad plus 12d squared equals a squared plus 6d plus 9d squared. And let's look at anything that, sorry, there should be an a in there. Anything that goes away, well, we have a squared and a squared on both sides, and then we want an expression for a in terms of d. So let's get everything with an a on one side and factorize out the a. We get a, actually factorizing is silly because we can just say that 8ad minus 6ad is 2ad, and on the other side we get minus 3d squared. D is not equal to 0, means we can divide by it, so 2a is equal to minus 3d, and therefore a is minus 3d over 2. How do we know that d is not equal to 0? Well, we are told so over here, and that's really important whenever you're going to divide. So that's the first bit done. Show that the fourth term of the geometric sequence is the 16th term of the arithmetic sequence. Well, the first thing we can do is we're going to find the next term of this sequence, and then we are going to find a16 and show that these things are the same. So let's find the fourth term of the GP first. And all we're going to do is take the third term, which is this, and multiply it by the common ratio. And the common ratio is really either this thing or this thing. I'm going to use this one, why not? Over a plus 3d. So it's the third term multiplied by the common ratio. In an instance where a is equal to minus 3 over 2d. So what we can do is we can substitute that into all of this stuff to see what we get. So we get minus 1.5d, minus 3 over 2d plus 6d is 4.5d, which is 9d over 2. In here we get minus 3 over 2d plus 12 over 2d is 9 over 2d. Minus 3 over 2d plus 6 over 2 is 3 over 2d. And obviously this simplifies in quite a nice way. So these d's go away, the divided by 2 goes away, and then we've got 9 on the top and 3 on the bottom, which is 3. Then we multiply this out, and that gives us 27d over 2. So it sort of looked really horrible at this stage, but actually it turned out to be something quite nice. We've got the fourth term of the GP, and now what we can do is work out the 18th term of the AP. Now, just to be precise, these things are equal. I'm going to write equals. The 18th term of the AP is A18, which is A plus 17d, and that's minus 3 over 2d plus 17 is 34 over 2, and so we get 31d over 2. And I've made a mistake. Whoops, I wanted the 16th term of the AP. My bad, let's correct that. So we want the 16th term, which is A16, which is A plus 15d. 15d is 30 over 2, and so we get 27 over 2 over 2d, which is the fourth term of the GP, because we found that there. Hooray, we're done. And I missed out a question, so I'm going to go back to it. An angle satisfies this equation, find the value of sec theta. Now, interestingly, we want to find sec theta. The way we remember the Pythagorean identities is we start off with sine squared theta plus cos squared theta equals 1, and we divide everything by cos squared, because then that gives us an expression for tan and sec. So this thing is tan squared theta, that's plus 1, and that's equal to sec squared theta. So tan squared is sec squared theta minus 1, minus 5 sec theta minus 10 is equal to 0, and this is clearly going to be a hidden quadratic in sec. So we've got this minus 5 sec theta minus 2 minus 10 is minus 12 is equal to 0. Now, some people might tell you to replace sec theta by something or other in order to solve the quadratic. I think you should just try and have a crack at it straight away. Okay, we're clearly going to have 2 sec theta and sec theta, and then we want two things that multiply to 12, where when you combine the terms appropriately, like this thing and this thing, or this thing and this thing, you get a 5 in the middle. Let's try 6 and 2. No, that doesn't work. Let's try 3 and 4. Ah, that could work. I think 2 by 4 is 8. 3 times 1 is 3, and the difference between 8 and 3 is 5. So I need that to be a minus and that to be a plus. This tells us that sec theta is equal to minus 3 over 2, or sec theta is equal to 4. Now, it says find the value of sec theta. So clearly, only one of these can be true. And if we scan back through the question, we see that theta is in the second quadrant. So maybe it's going to have something to do with what the signs of these are. Because if you think about the cos values, they're not a problem. This one is between 1 and minus 1. This one is between 1 and minus 1. So it's not going to be about saying, oh, cos is more than 1, which is impossible. In the second quadrant, remember that we go in this direction, anti-clockwise. We've got an angle which is over here, and that's the theta. So if we think about what the cosine is, the cosine in the second quadrant is going to be a plus number, because, nope, sorry, that's the sine. The cosine is going to be this distance over here, and that's clearly going to be a negative because we're in the negative x-axis, and therefore that's the value of sec theta, as sec theta must be less than 0. There we go.